Hello guys, welcome to this phenomenal experience. It's neurophysiology. I'm Charles and I'm reaching you live from PHCT in River State, Nigeria. Alright, in today's module we'll be looking at the tracts of the central nervous system. We shall do this under the following headings. First, introduction. Under introduction, we want to look at a nerve cell, what it is, the spinal cord, meaning of tracts, and then we'll proceed to look at the various types of tracts within the CNS, their functional differences or comparisons, and then we'll wrap it up by describing each of the parts or pathways of the central nervous system. Alright, good. Now, introduction. A nerve cell is the building block of the nervous system. Just like the cell is the building block of all living things. Nerve cells are the building block or the functional units of the nervous system. Structurally, a nerve cell looks like the rat in your kitchen. I hope you have seen a rat before. Of course, there are rats everywhere, even in Aso Rock. There was a time rats chased the president out of his office. So if you have not seen a rat before, just probably go to Chidima's house. She will show you one. Alright, so structurally, a nerve cell looks like a rat. This is a rat, a beautiful rat. Alright, now the body of the rat represents the soma. Now this is the body of the rat and it represents the soma. Soma simply means the body of a nerve cell. The four limbs of the rat represent the short processes of the nerve cell, which is known as dendrites. Okay, while the tail of the rat represents the axon. Okay, axons are the long processes of nerve cells. All right, good. All right, this rat also has a thigh and a speck. What does this represent? Alright, the thigh of the rat represents all medical and anatomy and physiology students. Alright, however, the glasses or speck of the rat represents all the optometry students. This rat it must be a very big man. Okay, now going forward, this is the structure of a nerve cell. The short processes here are known as dendrites. Okay, the long structure here is known as the axon of the neuron, whereas this rounded structure here is known as the soma or the body of a nerve cell. In the middle of the body, of course, you have a nucleus. Okay, good. We shall look at neurons in details when we get to nerve physiology. Alright. The spinal cord has two main parts. The first part is known as the gray matter, while the other part is known as the white matter. The structure here clearly shows the gray matter of the spinal cord, while this area clearly shows the white matter of the spinal cord. The gray matter is the colored butterfly-shaped part in the spinal cord. So this structure that is colored, that looks like a butterfly, is actually known as the gray matter of the spinal cord. It contains soma of neurons. All gray matters of the spinal cord contains only matter of neurons. Alright, they don't contain axons. They contain only the body of neurons. Okay, good. Going forward, the white matter is actually colorless. So this area represents the white matter of the spinal cord. Okay, white matter contains axons of neurons. Okay, beautiful. The gray matter of the spinal cord forms three horns. The first one is known as the dorsal or the posterior root horn. The second one is known as the ventral, also known as the anterior horn. And then the last one is known as the lateral root horn. This part of the spinal cord represents the dorsal horn. Okay, this part of the spinal cord represents the lateral horn. Okay, so this is the lateral root horn. All right, whereas this part of the spinal cord represents the ventral or the anterior horn of the spinal cord. These are the three main horns of the spinal cord. All right, fantastic. Now, the ventral and dorsal root horn anastomose or unite to form what is known as the trunk. Just a minute. This is the ventral root horn. It unites with the dorsal root horn to form the trunk. Alright, so this part of the spinal cord is known as the trunk. Alright, this area is known as the trunk. Now the trunk also divides into two parts to form what is known as the anterior and the posterior ramus. To form the anterior and the posterior rami. Now, going forward, good. The trunk, like I said, divides into two rami, the ventral ramus and the posterior ramus. Alright, the dorsal root horn contains only sensory neuron. Okay, there are two types of neuron. We have sensory neuron and motor neuron. Sensory neurons are neurons that carries information from all our body parts to the brain. Alright, whereas the ventral root horn contains only motor neuron. It doesn't contain sensory neurons. The motor neurons are neurons that carries motor command from the brain down to all body parts. Okay, good. We shall come to that as we proceed. Now, this is known as Bell-Maginte law. This law postulated that the dorsal horn of the spinal cord contains only sensory neuron, while the ventral root horn of the spinal cord contains only motor neuron. Alright, that is Bell-Maginte law. Alright, going forward. However, the trunk and the rami, that is the posterior and anterior ramus of the spinal cord, contains both sensory and motor neurons. Alright, good. The white matter of the spinal cord is also subdivided into three parts. These are the dorsal column, the lateral column, and the ventral column. Let me show you in a bit. This part of the cord, this part of the cord represents the dorsal column. Remember, this part is what? The dorsal horn. Alright, let me label it for you. This is dorsal horn. Okay, dorsal root horn is a part of the gray matter. Alright, remember the butterfly shaped part. Now we are talking of the different parts of the white matter. First part is the dorsal column, and this area represents the dorsal column of the spinal cord. This part represents the lateral column, whereas this part of the cord represents what? The ventral column. Remember, this is the lateral root horn. This is what? The ventral root horn. And this part is the dorsal root horn. I hope that is understood. Alright, going forward. Tracts. What are tracts? Okay, tracts are collection of axons within the CNS. Take notes. The axons are in capital letters. Tracts are not collection of dendrites of neurons. They are also not collection of soma of neuron, whereas they are collection of axons within the CNS. They are collection of rat tails. Alright, going forward, they are also parts of the white matter of the spinal cord. All axons of neurons lie within the white matter of the spinal cord, whereas the soma and some dendrites of the neuron lies within the gray matter, that is the butterfly shaped structure of the spinal cord. Alright, good. Now, there are two types of tracts. These are ascending tracts and the descending tracts. Ascending tracts are tracts that carries sensory information from all our body parts to the brain. So they are coming from down to the higher centers. Alright? Whereas descending tracts are tracts that carries motor command from the brain to the body parts. So descending tracts, look, names have meaning. Ascending. These tracts are moving from our body parts to the higher centers, the brain. They are going upwards. Whereas descending tracts are tracts that are moving from the higher centers down to all our body parts. It's very, very simple. From their names, you will be able to define these two important tracts of the CNS. Going forward, ascending tracts are somatosensory tracts. Somatosensory simply means they carry sensory information to the somatosensory cortex. The somatosensory cortex is found at the parietal lobe of the cerebral cortex. Alright, so they are sensory tracts. It means that if I touch you, you feel it. You are able to recognize that I have touched you because this tract has carried that stimulus for touch from wherever I touched you, whether it was your hand or your leg or your arm. It's carrying that information straight from that part to the brain. Then you can feel it. Alright? Ascending tracts carries information from all our body parts to the CNS. Alright? Good. Now, there are two subdivisions of the ascending tracts. The first one is known as the dorsal column-medial lemniscal system or pathway. The second one is known as the spinal column lemniscal system. Okay, let's look at the differences between the dorsal and the spinal column lemniscal pathway. We'll begin with the dorsal column lemniscal system. This system has two subdivisions. The first one is the fasciculus gracilis system, and the second one is known as the fasciculus cuneatus system. Alright, they are modern pathways. These pathways are modern pathways. They are not primitive but modern. Alright, good. Now, these tracts also have high conduction velocity. It means that the information from all body parts gets to the brain or the higher centers with speed, with a very high conduction velocity. Okay, good. Now, one striking feature of these tracts is that they are highly myelinated. Alright, and that is why the conduction velocity is high. This is because action potentials in myelinated neurons are transmitted very fast. Okay, so any neuron that is myelinated, you know that the conduction of action potential is very high. Hence, the conduction velocity of these tracts are high. The sensations carried by these tracts are well localized at the CNS. Alright? What do I mean? If, for example, I prick Ogene with a pin, she will feel it immediately in her head that, well, something just choked me. Now, not only that, Ogene will be able to pinpoint exactly where she's feeling that pain. Now, if you go to the hospital and you are asked by the doctor where exactly is paining you, and you are able to pinpoint the place or the area or the part of the body that you're having a pain, that pain is very well localized in the brain. But in most cases, when people go to the hospital and the doctor asks, okay, where are you having this pain? They say, doctor, it's around here, my abdomen region. That pain is not well localized at the CNS. Alright? So whenever you're not able to pinpoint where you are having a pain or where something is hurting you, that pain is poorly localized in the brain. All right, but all the sensations carried by the dorsal column medial lemniscal pathway are well localized in the brain. All right, good. Going forward. All right, for the spinal column lemniscal system, it is also divided into two parts. The first one is known as the ventral spinothalamic system, also known as the anterior spinothalamic system. The second one is the lateral spinothalamic system. This system is primitive. It has been there even before we were born. Alright? Good. It has a low conduction velocity, and that is because they are moderately myelinated. Alright? There are two types of neurons. We have the myelinated neurons and the unmyelinated neuron. The conduction speeds in myelinated neurons are high, they are fast, whereas the conduction velocity of unmyelinated neurons are not fast, they are very, very slow. There's what we call saltatory conduction of action potential. Alright, we're going to do that in nerve physiology going forward. Now, sensations carried by this system are poorly localized. It means that you are not able to pinpoint where you are having that feeling or that sensation or that pain. Alright, so they are poorly localized. Good. Going forward, the dorsal column lemniscal system carries sensory information for fine touch. Fine touch, an example is like pricking someone with a pin, okay, or when you have a knife cut, okay, fine touch. These type of sensations are well localized in the brain, and that is why whenever you have an accident, you'll be able to pinpoint where you are having pains, maybe from injured tissues, cuts. If I use a sharp knife to cut Obina's hand, of course he's going to scream. You know, the sensation goes straight to the brain and with a very high conduction speed. Alright, so this type of sensation, fine touches, that is carried by the dorsal column lemniscal system. Alright, good. Now, it also carries information for proprioception. Proprioception simply means the information coming from the joints, the tendons, the muscles, information about position, postures, and movements. These are proprioceptive information. Okay, it also carries information for 2-point discrimination and vibration. All right, for the spinal column lemniscal system, they carry information for crude touch, such as itching and tickling. These are crude touches. All right, fantastic. This system also carries information for pain, specifically the lateral column, the lateral spinothalamic tract carries information for pain. All right, good. It carries information for temperature and pressure. It also carries sexual sensations. Yeah, you know, sex is also a kind of sensation. All right, and sexual feelings or information, that is when you are having coitus with your husband, or of course your husband, you should be having sex if you are not married. Sexual information are carried by this system. All right, if you ask the married women, they tell you that sex is sweet and is bitter. Well, I don't know, I'm not married. I've not done it before. I've not even hugged a girl before in my life since I was born. All right, so but those of you who are married, who have had sex before, you can tell us, is it sweet or painful or both? All right, but the thing there is that basically sexual sensations are carried by the spinal column lemniscal system. Remember I told you the spinal column lemniscal system is a primitive system. So sexual sensations, sex has been going on right from time immemorial, even before you and I were born. Of course, you are all products of people who made love many years ago. Shall now look at dorsal column medial lemniscal system in details. All right. This diagram summarizes the dorsal column-medial lemniscal pathway. We shall look at that in details going forward. The nerve fibers mediating fine touch, proprioception, 2-point discrimination and vibration actually enters the spinal cord through the dorsal root horn. The dorsal root horn is a component of the gray matter. So sensory information or sensory nerve fibers carries information from all body parts to the cord and then the CNS by first passing through the dorsal root horn of the cord. Now, the further ascent in the dorsal column of the spinal cord. These fibers now divide into two parts. The first part is known as the fasciculus gracilis, which forms the medial part. This part is the medial part. It is the medial part because it is closer to the midline. This is the midline of the cord. So it is actually lying medial to the midline of the spinal cord. So the medial part or the medial division of this fiber is known as the fasciculus gracilis. Alright, and the other part is known as the fasciculus cuneatus, which is the lateral part. This part is the lateral part or lateral division of the dorsal column lemniscal fibers. Alright, functionally, the fasciculus gracilis carries information from the legs and lower parts of the body to the CNS, whereas the fasciculus cuneatus carries information from the hands and upper parts of the body into the spinal cord and then to the CNS. Alright, good. Now, the electrical stimulation of the fasciculus gracilis would cause sensations in the leg and lower parts of the body. Alright, good. Whereas electrical stimulation of the fasciculus cuneatus would cause sensations in the hand and the upper parts of the human body. It means that if I stimulate these parts, the medial part or the medial fiber of the dorsal column medial system, you would feel the sensation in your legs and upper parts of the body. Conversely, if I stimulate the lateral part, that is the fasciculus cuneatus, electrically, sensations are felt around the hand and the upper part of the body. It's very easy to remember these two divisions of the dorsal column lemniscal system. First, you could say legs are gracious. Alright, legs are gracious. It simply means the fasciculus gracilis, they carry information from the legs and lower parts of the body, and electrical stimulation of that fiber would cause sensations around the legs and lower parts of the body. So legs are gracious. Are your legs gracious? Of course, mine are gracious. If your legs are not gracious and sexy and beautiful, my own legs are gracious. Alright, good. Now, the other way to know this, the fasciculus cuneatus, you could say hands are cute. It simply means that these fibers carries information from the hand and the upper parts of the body to the CNS. Are your hands cute? Oh, I have a cute hand. You can see? Alright, my hands are cute. I don't know about your hands. So, legs are gracious, hands are cute. That is the key for recalling these two divisions of the dorsal column lemniscal pathway. Going forward, now, both the fasciculus gracilis and the fasciculus cuneatus ascend the cords ipsilaterally, that is on the same side, right? They ascend the cords ipsilaterally on the same side to reach the medulla oblongata. This part is the medulla oblongata, right? So this part is the medulla oblongata. The whole of this part represents the medulla oblongata. Alright? Good. Going forward. Now, I said both parts ascend the cord ipsilaterally. The word ipsilaterally means on the same side. you can see that the fasciculus cuneatus and the fasciculus gracilis divisions of the dorsal column system, they actually ascend the cord on the same side to reach the medulla. Okay, good. Now in the medulla oblongata, certain events occur. First is that the fasciculus gracialis synapse or unites with its nucleus, which is known as the nucleus gracialis. Alright, here is the fasciculus gracialis, and this is the nucleus of the fasciculus gracialis. So fibers of the fasciculus gracialis unite with its nucleus, the gracialis nucleus. Alright, also the fasciculus cuneatus synapse with its nucleus, which is known as the cuneatus nucleus. Alright, this event occurs in the medulla. That is one. There are other things going on in the medulla. Alright, now both fibers decussate to the opposite side. Now fibers of the fasciculus cuneatus and the fasciculus gracialis, after synapsing with their respective nucleus, they decussate. It means they cross over. The defects, if I want to use the language of politicians, they defect to the opposite side of the cord and begin to ascend contralaterally on the opposite side. Now, the fiber started from this point. Alright, when they get to the medulla, they synapse with their respective nucleus and then they cross over the midline to the opposite side of the cord. This crossing over, this is the midline. Alright, this crossing over of both fibers to the other side or opposite side of the cord is known as decussation. Alright, defection. Alright, good. Going forward, now both fibers now fuses together to form the medial lemniscal system. Alright, this is still occurring within the medulla oblongata. Now after decussation, they fuse together to form what? The medial lemniscal system. Alright, good. This is the medial lemniscal system. This is actually the medial lemniscal system. Alright, fantastic. So going forward, the formation of the medial lemniscal system actually gives rise to the name dorsal column medial lemniscal system or pathway. This is where the names are derived from. Alright, going forward. Now, to summarize the events occurring in the medulla. Firstly, the two fibers synapse with their respective nucleus. Alright, both fibers now decussate. They cross over to the opposite side of the cord. Thirdly, the two fibers fuse together to form the medial lemniscal system. Formation of the medial lemniscal system gives rise to the name of this pathway, which is the dorsal column medial lemniscal system. Alright, okay, going forward. Now, the fibers of the medial lemniscal system further ascends. This is the medial lemniscal system. It further ascends the pons, the midbrain, and the thalamus to reach where? The somatosensory cortex. Now, this area, we have this area, the pons, the midbrain, okay, and this is the thalamus. Okay, I'm just trying to make things clearer for you. This is, of course, the medulla. This part is the pons, and this other part is what? The midbrain. Alright, this is pons, the pons. Alright, good. So the fibers ascend through the pons, the medulla. It passes through the thalamus. Of course, they are also relayed in the thalamus. The thalamus is the area where information are relayed to reach the somatosensory cortex. This is the somatosensory cortex. Alright, good. This is the terminal point of the dorsal column lemniscal pathway or system. Very interesting, isn't it? Alright, for the spinal column lemniscal pathway or system, I told you that this pathway has two divisions, the lateral spinothalamic tract and the anterior or the ventral spinothalamic tract. Okay, good. Now, the nerve fiber mediating crude touch is the anterior spinothalamic tract, whereas the nerve fiber that is carrying pain, pressure is and temperature, pain, pressure, and temperature is actually the lateral spinothalamic tract. For the anterior spinothalamic tract, nerve fibers mediating or carrying crude touch also enters through the dorsal root horn of the spinal cord. Now, when it enters the spinal cord, it decussates to the anterior column of the cord. It means that, look, this fiber mediating crude touch, the anterior spinothalamic tract, okay, enters through the dorsal root horn of the spinal cord. Remember, this is the midline. Let me make that clearer. There's a midline here. Okay, look, this is the right side of the cord, this is the left side of the cord. Okay, this is, let's call this right, and this is left side of the cord. Alright, now the fibers mediating crude touch enters through the right dorsal root horn of the spinal cord. When it gets here, it crosses the midline to the opposite side of the spinal cord. Okay, that is decussation. It then ascends as the anterior or the ventral spinothalamic tract. Okay, good. Alright, this is the anterior spinothalamic tract. ASTT means anterior spinothalamic tract. Also know that it is called ventral spinothalamic tract. In the same way, the nerve fiber mediating pain and temperature also enters the dorsal root horn of the spinal cord. When it gets here, it also decussates to the opposite side of the cord and ascends as the lateral spinothalamic tract. Take note that the lateral spinothalamic tract decussates from the right to the left side of the cord to enter the lateral column of the spinal cord. That is the lateral component of the white matter of the spinal cord. That is where they derive their names from. If this decussation goes to the ventral column of the cord, then the name will be ventral spinothalamic tract. If it goes to the dorsal column of the cord, then the name will be dorsal spinothalamic tract. But because it enters to the lateral column of the spinal cord, the name is lateral spinothalamic tract. In the same way, the anterior fiber enters through the dorsal root horn of the cord, decussates to the anterior column of the spinal cord. Hence, the name is anterior spinothalamic tract. Alright, now there are two things you need to know. The first one is that for the dorsal column lemniscal system, the decussation of the fasciculus gracilis and fasciculus cuneatus occur in the medulla. Alright, but for the spinal column lemniscal system, decussations are taking place at the spinal cord, not the medulla. Alright, so you can see the crossing over is within the spinal cord. Alright, just take note of that going forward. Both the anterior spinothalamic tract and the lateral spinothalamic tract fibers ascend the cord to reach the medulla. In the medulla, both tracts synapse to form the spinal column lemniscal system. This is the spinal lemniscus. Hence the name spinal column lemniscal system. The spinal column lemniscal system further ascends the pons, the midbrain, the thalamus, and terminates at the somatosensory cortex. All right, good. Now, take note that the pain fibers gives rise to branches, such as the cingulate gyrus of the limbic system, the insular cortex, and the reticular formation. Now, this is important because these branches are responsible for the emotional components that is associated with pain. The limbic system, like I said in previous novel, controls emotions. So, when the pain fiber gives a branch to the limbic system, alright, the patient at that point is very, very emotional. And that is the reason why when a patient is in pain, they keep shouting, "Hey, doctor, my ayo, where is doctor? Hey, yo." You know, at that point, that patient wants to hear, "Sorry, you'll be fine." As a doctor or a professional, you are expected to give hope to your patients whenever they are in pain, because pain has a heavy emotional component. We shall talk more on that when we treat physiology of pain. Also, the insular cortex is responsible for the increased heart rate and increased respiratory rates, including sweating and vomiting that is associated with severe pains in patients. Alright, so a patient in pain has a very high heart rate, he breathes very fast. That is one of the signs you know when a patient is in a very severe pain. So the pain fibers are also giving branches to the insular cortex. It also gives branches to the reticular formation. I mentioned this in a previous model. Alright, and this reticular formation is responsible for the sleeplessness and alertness that is associated to pains. Alright, so a patient in pain cannot sleep because the pain fibers always give collateral to the reticular formation, keeping that patient awake and screaming. Alright, good. Going forward. Now, the descending tracts of the CNS. These tracts are motor tracts. They carry motor information from the brain down to the body parts. Remember, the ascending tract carries sensory information. Please take note. I said sensory information. Ascending tract carries sensory information from all body parts to the brain, whereas descending tract carries motor information from the brain to all our body parts. Alright, going forward, there are two types of ascending tract. The first one is the pyramidal tract and the extrapyramidal tract. Okay, good. The physiological differences. This column represents the pyramidal tract, while this one represents what? The extrapyramidal tract. So there are three main types of pyramidal tracts. The first one is the lateral corticospinal tract. The second one is the ventral corticospinal tract. And then the last one is the corticobulbar tract. Alright? Whereas for the extrapyramidal tracts, there are many of them, but there are four major ones. These are the rebrospinal tract, the vestibulospinal, the reticulospinal, and the tectospinal tract. These are the main tracts of the extrapyramidal system. Alright? Now, these pyramidal tracts are located in the precentral gyrus. Alright? Good. They descend directly from the cerebral cortex to the spinal cord. I said all descending tracts carries information from the upper or the higher centers down to the body parts. Alright? 80% of the pyramidal tracts cross the medulla or decussate in the medulla, whereas 20% decussates at the level of the spinal cord. Okay, good. Now, the functions of pyramidal tract is that, look, they control skilled or fine movements. Okay, skilled or fine movements. That is, they actually innervate muscles of the distal limb, the muscles around your wrist, the ankle, and so on and so forth. Examples of skilled or fine movements include dribbling in a football match. Okay, typing, writing. Writing is a skilled movement. Alright, good. Acrobatic dances. Alright, these things are skilled movement. Playing of organ or keyboard in the church, they are skilled movement. Alright, good. So it is the pyramidal tracts that are controlling skilled movements. That is the lateral aspects or components of the pyramidal tract. Alright, whereas the ventral aspect controls muscles of the proximal limbs. Alright, so they are involved in posture and postural adjustments. Okay, Now, for the extrapyramidal tract, I said there are 4 types. Okay, they originate in the brainstem nuclei. Okay, good. No direct control of motor cortex. The functions of the extrapyramidal tract is that they are specifically important in the control of posture and postural adjustment. These tracts innervate the proximal limb muscles. Okay, they help us to maintain posture and balance during movement. All right, going forward. The corticospinal tract. The diagram here shows the corticospinal tract. All right, the ventral corticospinal tract starts from the brain and descends to reach the medulla. In the medulla, it does not decussate. It continues ipsilaterally, that is on the same side, to reach the spinal cord. Now, when it gets to the spinal cord, the decussation occurs. So it crosses the midline to the opposite side of the cord and then terminates at the effector organ, which is the muscle. Okay, remember we have our midline here. The midline is here. Okay, our midline is very important. We know this. Okay, this is our midline. Okay, the medulla also have pyramids. I will just use a triangle to depict that. This is medullary pyramids. Okay, now the lateral corticospinal tract also starts from the brain. It descends to reach the medulla. At the medulla, it passes through the medullary pyramids. All right. Okay, another thing also happens in the medulla. After passing through the medullary pyramid, it decussates. It crosses the midline to the opposite side of the cord. This is lateral corticospinal tract. Okay, and then descends contralaterally and finally terminates at the effector organ, which is the skeletal muscle. Okay, look, ventral descends and the point of decussation or crossing over is in the spinal cord. Okay, it doesn't pass through the medullary pyramid. That is for ventral corticospinal tract. Whereas the lateral descends, it passes through the medullary pyramids. It then decussates in the medulla. Take note, the point of decussation for lateral corticospinal tract is the medulla. It also passes through the medullary pyramids. However, the point of decussation for the ventral corticospinal tract is at the spinal cord. It does not pass through the medullary pyramids. Alright, good. Going forward. Now, let's look at this beautiful tract in details. The corticospinal tract actually originates in the motor cortex. Okay, good. Fibers descend through the internal capsule. This is the internal capsule. These areas are the right and left internal capsule. So the fibers descend through the internal capsule. It passes through the midbrain. This is the midbrain. My marker. This is the midbrain. Alright. It also passes through the pons. This is the pons. Okay. The pons is this area here. This one is the cerebellum. The cerebellum is just behind the brain, the brainstem. Okay. Now, it also descends through the medulla oblongata. All right, and then finally to reach the spinal cord, which then terminates at the effector organ. Okay, good. Now going forward. It descends the midbrain and the pons, and also the medulla oblongata. Okay, good. Now in the medullary pyramids, okay, the corticospinal tract actually divides into two. The lateral corticospinal tract, which forms 80% of the fibers, okay, and then the anterior corticospinal tract, which forms 20% of the corticospinal tract fibers. All right, good. The lateral corticospinal tract decussates and descends contralaterally into the cord to supply the muscle. I said that earlier. So it decussates and descends contralaterally. Look, it was actually descending ipsilaterally, that is on the same side of the cord. This is lateral corticospinal tract descending ipsilaterally. It descends the midbrain, the pons, and the medulla ipsilaterally, that is on the same side of the cord. Then when it gets to the medulla, it passes through the medullary pyramids, like I said earlier, and then decussates to the opposite side of the cord and begin to descend downwards contralaterally, which then terminates at the skeletal muscle. Okay, going forward now. Functionally, the lateral corticospinal tract controls distal muscles. Okay, so they are very, very important for regulating skilled movements such as grasping of small objects, writing, typing, playing organ or keyboard, dribbling in a football match. I've said that before in this class. Alright, the anterior corticospinal tract forms only 20% of the fibers of the corticospinal tract. Okay, good. They descend ipsilaterally into the cord. This is the anterior. It descends on the same side of the cord, the midbrain, the pons, and the medulla ipsilaterally, that is on the same side. Okay, finally it decussates to the contralateral side of the cord to supply the muscles. Look, where is the point of decussation? It is still descending ipsilaterally, but when it finally gets to the spinal cord, it decussates, crosses over to the opposite side, and terminates at the skeletal muscle fiber. Alright, good. Functionally, the anterior corticospinal tract controls muscles of the proximal limb, so they are important in gross movements and then postural adjustment. Alright, the extrapyramidal tract, they originate from the brainstem nuclei. Okay, I told you there are 4 major types. There are many of them, but the 4 major types are the vestibulospinal tract, the reticulospinal tract, the rebrospinal tract, and the tectospinal tract. These are the 4 major types of the extrapyramidal tract. Now, this diagram shows the pathway for the 4 major types of the extrapyramidal tract. This is the rebrospinal tract. Okay, from here down to this part is the reticulospinal tract. This one is the vestibulospinal tract. Okay, from here down to here represents the vestibulospinal tract. From here, the superior colliculus down to this part represents the tectospinal tract. And then from the red nucleus, this part down to this part represents the rebrospinal tract. Now, 2 of these tracts descend ipsilaterally down the spinal cord to end and the effector organ, which is the skeletal muscle. The tracts are the reticulospinal tract and the vestibulospinal tract. They do not decussate, alright, at any point within the CNS. Whereas 2 decussate or cross over the midline to the opposite side of the CNS. The tracts are the rebrospinal tract. As you can see, it starts from the red nucleus in the midbrain, and it decussates to the opposite side of the cord and begins to descend contralaterally down to the spinal cord. The same thing with the tectospinal tract. Alright, it starts from the superior colliculus and then descends. It was descending ipsilaterally, that is on the same side of the CNS, and then decussates to the opposite side of the CNS and begins to descend contralaterally and finally terminates at the effector organ. So, rubro and tecto decussates at some point within the CNS, whereas the vestibulo and reticulo tract does not decussate at any point within the CNS. We shall look at these tracts one after the other, tracing their pathways and their origins, their pathways and their functions. Okay, good. Now, This tract actually controls involuntary and automatic movement. Take note of that. Good. The vestibulospinal tract. It originates from the vestibular nuclei of the pons. This is the vestibular nucleus. Okay? And this is the pons. Alright, so it's taking its origin from the vestibular nucleus. And that is where it derives its name from, vestibulospinal tract, because it originates from the vestibular nucleus and descends down to the spinal cord where it terminates. So vestibulospinal tract. Alright, going forward. Good. It receives inputs actually from the PC of the cerebellum, that is from the Purkinje cells of the cerebellum. Alright, it also receives inputs from the vestibular apparatus of the middle ear. When we treat cerebellum, I'm going to show you all the cells of the cerebellum and explain their specific functions. But for now, this vestibulospinal tract receives inputs majorly from the Purkinje cells of the cerebellum and vestibular apparatus of the middle ear. Alright, it descends ipsilaterally, that is from its point of origin, it descends ipsilaterally on the same side of the cord. Okay, and then terminates at the skeletal muscle, and its main function is to control balance and postural adjustments. Alright, fantastic. Now, the reticulospinal tract actually originates from the reticular formation or the reticular nuclei of the medulla. This is actually the reticular formation. Okay, the purple colored structure represents the reticular formation. So it's taking its origin from this part of the CNS, the the reticular formation. This tract receives inputs or information from all parts of the CNS. I told you that the reticular formation sends branches to all parts of the CNS. So it receives inputs, information from all parts of the CNS. Alright, it then descends ipsilaterally, just like the vestibulospinal tract, into the cord, and it terminates at the skeletal muscle where it enhances movements going forward. Now, the rebrospinal tract originates from the red nucleus of the midbrain. This is the red nucleus. Alright, fantastic. It receives inputs from the deep cerebellar nuclei of the cerebellum. Again, I'm going to treat that when we do physiology of the cerebellum. And then it decussates at the midbrain and descends contralaterally to the cord, where it terminates at the skeletal muscle. It controls skewed and gross movement. Going forward, the tectospinal tract originates from where? The superior and the inferior colliculus, which is located where? At the midbrain. Okay, good. It receives input from the optic nerves. Now, this tract actually controls movement of the eye, and it has to do with sensory information and motor commands of the eye. This tract is a tract that the OPT students are supposed to study very well, okay, because it has to do with the eye, tectospinal tract. Alright, so it receives input from the optic nerves, okay. It also receives input from the deep cerebellar nuclei. Okay, good. Now, this tract descends contralaterally. Where is the tract? Look. Firstly, it descends ipsilaterally in the CNS, and it decussates to the opposite side of the CNS and begins to descend what? Contralaterally. That is, it begins to descend downwards and terminates at the effector organ, which is skeletal muscle. Functionally, this tract controls movements of the head. So when your head is turning front and back, side and sideways, you are shaking your head the way Wike was telling one chief in Port Harcourt, River State. You are shaking your head like a lizard. It's man than foot. So when the head is shaking, like this, you know that the tectospinal tract is playing a major role in that head movement in relation to visual stimulus. Okay, so your head can turn in relation to the information coming from the eye. That is the specific function of the tectospinal tract. Alright? Alright. We have come to the end of module 3. Okay? So the quiz for today is a very simple one. You just juxtapose upper and lower motor regions. Okay? You do that and submit before the next lecture. Alright? Good. Up next is ANS physiology. So in our next module, we'll be looking at the physiology of the autonomic nervous system. Thank you so much for staying tuned. I remain Charles, the anchor and facilitator for this course. Bye. Bye.